Okay, so this is the start of section 15.5. It is on curl and divergence, and in this video, we're just going to focus on curl. So the curl of a vector field um, gives another vector field. So the curl, this is something that's just defined for three-dimensional vector fields. So vector fields on R3. So let F uh, be a vector field on R3. Then the curl of F is equal. This is going to be weird when I write this. The gradient operator crossed with the vector field. So this takes some explanation. Okay, so let's say F is a vector field, and its components are P, Q, and R. So the curl of F is equal to the determinant of the following matrix. This is I, this is J, this is K. Sorry, let me make that a little better. And here, okay, so these are vectors, but here instead of putting numbers, we're going to put partial differential operators. So that means the partial derivative with respect to x. This is the partial derivative with respect to y, partial derivative with respect to z, and now we'll put the components p, q, r. Okay, so what you do then is, like, the first component of this vector is going to be the partial derivative of r with respect to y minus a partial derivative of z with respect to q. Okay, and so we're going to look at an example. So let's say that we have some vector field. It's equal to x squared y. The second component can be z. Come on. And the third component we'll just say is equal to 1. Okay, then the curl of f is equal to the following: I, j, k. This is the partial x derivative. This is the partial y derivative. This is the partial z derivative. Here we put the p function. This is x squared y. Here we put the z function, and here we put the q function, and here's the r function. Okay, so this is p, this is q, this is r. This is p, this is q, this is r. Okay, so this is going to be I times the determinant of this 2 by 2 matrix. So it's the partial derivative of 1 with respect to y minus a partial derivative of z with respect to z. So that's just going to be minus 1. Okay, now for the next one, it's minus j. So really, these should all have hats, but I'll be lazy with that probably. So it's minus j times the determinant of this 2 by 2 matrix. So it's the partial derivative of x with respect to the partial derivative of 1 with respect to x minus the partial derivative of x squared y with respect to z, which is 0. And then plus k hat is going to be the determinant of this 2 by 2 matrix. So it's the partial derivative of z with respect to x, which is 0, minus the partial derivative of x squared y with respect to y, which is minus x squared. Okay, so this then is just minus 1, 0, minus x squared. So the curl of this vector field is equal to this vector field. So the curve of a vector field on R3 is another vector field on R3. Okay, so let's say f is conservative. In other words, f is a vector field, is the gradient of some function little f. Let's compute the curl. So the curl of f is going to be the following. It's going to be this determinant I, j, k, the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. This will be fx, fy, fz. Okay, so what is this? This is going to be I times the determinant of this 2 by 2 matrix. So this is the partial derivative of fz with respect to y minus the partial derivative of fy with respect to z. Okay, minus minus j hat times this 2 by 2 matrix. So it's going to be um, the partial derivative of fc with respect to x minus the partial derivative with respect to z of fx plus k hat times the determinant of this 2 by 2 matrix, this one. So this is the partial derivative of x, the partial derivative of fy with respect to x minus the partial derivative of fx with respect to y. Okay, and just if you haven't caught on yet, this notation, this notation, d sub x, this is just another notation for this. Okay, and similarly with the y's and the z's. Okay, it's just a more convenient notation, I guess. Right, one less thing. Okay, so let's look at this one. So this is the partial derivative of fz with respect to y. So this right here, this function here is fzy, and this function here is fyz. Well, by Clairaut's theorem, these are equal. So this term is equal to 0. And similarly for these terms, this is fzx, this is fxz. By Clairaut's theorem, these two terms are equal, so this component is equal to 0. And similarly down here, this is fyx, this is fxy. These two terms are equal, so this is 0. Okay, so what this means is that whenever f is conservative, then its curl is equal to 0. So let me write that now. Okay, so what we just saw was that if f is conservative, then the curl of f is equal to 0. And there's a converse to this theorem. And the converse says that, here's another fact. So if f is defined on all of R3 and its components have continuous derivatives and the curl of f is equal to 0, then f is conservative. Okay, so the main part of the statement says that if the curl of f is equal to 0, then f is conservative. Okay, so this is similar to what we saw before. If this, when we had a vector field on R2, if the components Q and P satisfied some property, then we knew that it was conservative. Okay, and we have something, the analogous thing here says that if the curl of f is equal to 0, then f is conservative. Okay, so this gives a way for us to check whether or not a given vector field is conservative. And that's what we're going to do next. And we're also going to look at a way to construct a potential given a conservative vector field. Let's say this is our vector field. This is the determinant that we have to compute to find the curl. So the thing that goes here is going to be the determinant of this 2 by 2 matrix. So the determinant of this with respect to y is 3x squared z squared. The determinant of this with respect to z is 3x squared z squared. The next component is going to be minus the determinant of this 2 by 2 matrix. So this is going to be, well, it should be the partial derivative of this with respect to x minus the partial derivative of that with respect to z. But since it's minus, we'll do it the opposite. So it's the partial derivative of this with respect to z. That's 6xy z squared minus the partial derivative of this with respect to x. So this is minus 6xy z squared. And finally, the last component is going to be the determinant of this 2 by 2 matrix. The derivative of this with respect to x is 2x z cubed. And the determinant of this with respect to z is the determinant of this with respect to y is 2x z cubed. Okay, and this is equal to 0 because all of these terms are equal to each other. So this is equal to the 0 vector. Okay, so this tells us that f is conservative. And so now we want to find a potential. In other words, a function such that big F is equal to the gradient of that function. Okay, so we want a function little f such that big F is equal to the gradient of little f. Okay, so we know that this component is f sub x, this component is f sub y, this component is f sub z. So this is going to be similar to how we found a potential before. So we're going to start by saying, well, if this is true, then this is going to be the antiderivative of 2xy z cubed dx plus a constant of integration, but now the constant has to be a function of y and z. Okay, because the derivative of this with respect to x is equal to 0. So this is going to be x squared y z cubed plus some unknown function g of yz. Okay, now the partial derivative of f with respect to y, we know from this that it's equal to x squared z cubed plus cosine y, but the partial derivative of this with respect to y is x squared z cubed plus the partial derivative of g with respect to y. Okay, so setting these two equal to each other, it says that the partial derivative of g with respect to y is equal to cosine y. So this says that g of yz is equal to sine y plus some unknown function of z. That's just the constant of integration. Gy is equal to cosine y, so we take the antiderivative of both sides with respect to y. G of yz is equal to sine y plus some function of y, or z. Okay, so now the partial derivative of f with respect to z, we know is equal to this. So this is equal to 3x squared y z squared plus e to the z. That's just the z component of the vector field. But we also know that it is equal to the partial derivative of this f with respect to z. Okay, so the partial derivative of this with respect to z is 3x squared y z squared plus the partial derivative of g with respect to z. The partial derivative, or sorry, the partial derivative of g with respect to g, the partial derivative of g with respect to g, with respect to z, wow. But g is equal to sine of y plus some function of z. So this is just going to be plus h prime of z. Okay, so this tells us that h prime of z is equal to e to the z. So in other words, h of z is equal to e to the z plus some constant c. Okay, so overall, all of this tells us that f of x, y, z is equal to x squared y z cubed plus g of yz. G of yz is sine of y plus h of z. H of z is e to the z plus c. So this is plus sine y plus e to the z plus c. So any function of this form, in other words, for any constant you want to put here, all of those functions, the gradient of any of these functions, no matter what constant you put here, is going to be this vector field. Okay, and again, this is very similar, except there's a couple more steps to when we were finding. This is very similar to when we were finding potentials when we were dealing with two-dimensional vector fields. So, of course, you might not get this. Watch the video again and do a bunch of practice problems.